Hello, everybody. Hello, and welcome. My name is Stephen Hummel. I'm Dark Sky Specialist here at McDonald Observatory. Welcome to our live Deep Sky Tour, and also happy International Dark Sky Week. Hopefully, you are doing something for Dark Sky Week. This could be one of those things, but I also encourage you to get outside and enjoy the sky for yourself this week, especially. But I am here at McDonald Observatory, and McDonald Observatory is in far west Texas. And I'm coming to you live from the dome with the arrow at it. That dome houses a 16-inch telescope, which is located right behind me. And that telescope is what I'm going to be using tonight to show you some live views of a few objects in the sky. And if you are curious about the specifics, if you're a telescope nerd like I am, you can find all those details in the description below this video. But I'm also joined tonight by Bill Wren. Hi, Bill.
Hello, everybody. Hi, Stephen. I'm Bill, and I'm an assistant to the superintendent at McDonald Observatory, and my job is basically to keep the skies dark. It's great to be here with y'all and with Stephen on Dark Sky Week.
Yeah, it's great to have you, Bill. Thank you for joining me on this program. It's always a pleasure. I do want to add before we get started tonight that if you have any questions for myself or Bill throughout the program, you are welcome to answer them in the live chat, if you're watching this live, that is. And there are also moderators in the chat to assist you on some questions. They'll answer a few, and if they think your question is good or would take too long to write out in the text and chat, they will forward it along to me and Bill, and we'll take them at the end. And tonight we have some fantastic skies. We have really good conditions all around, basically as good as you could reasonably ask for. Not too cold, not too hot, nice 62 degrees Fahrenheit. Stars are starting to come out. The last little bit of twilight's fading away, and very low humidity, very low wind, just all around great night. And you can see in this live all-sky camera view of the sky that even though it's not totally dark, you can see quite a few stars. And that's, of course, because we have dark skies here at McDonald Observatory. It is one of the things that really sets us apart from other observatories, is that we have some of the darkest skies of any major observatory in the United States. And, of course, that makes a really big difference in what you can see. Isn't that right, Bill?
Yes, it is. Steve is displaying a map from an atlas of artificial sky glow. That's actually data that was taken in 2014 and processed. The satellite imagery was processed through some software that draws in the sky glow contours, so you can see where there are dark skies and where it's black. And then, well, basically, if you can pick out Interstate 35, the San Antonio, Austin, Dallas corridor, there basically everything east of I-35 is toast. The places you can go to see a naturally dark nighttime sky are rapidly shrinking and becoming fewer and farther between. And we'll be talking about how we're working to try and keep the skies dark here for ongoing astronomical research at McDonald Observatory.
Yeah, so here is a view of what the sky sort of looks like right now. Is basically real time. And Bill, yeah.
Yeah. This is basically what the sky would look like in a rural community. We'd see a few more stars here at McDonald. It's a little darker, but as you get closer to urban centers, the sky glow increases and the number of faint stars that you see are lost. This would be what you might see in a suburban neighborhood, and then by the time you get inner city, you're lucky to see a dozen stars altogether.
Right. So obviously, being far from major cities makes a big impact. But even though the skies are dark here, it's not just dark because we're in a rural area. Really, it's dark because we work with the surrounding communities to keep the sky dark. Because there are ways to address light pollution. There are solutions, which we're going to talk about later on. But the first object that we're going to look at tonight in the telescope is probably the easiest object to see in the night sky, aside from the moon or some planets. It is the brightest star in the sky. Sirius. Sirius with an I is the brightest star of Canis Major, and it's the brightest nighttime star in the sky. Of course, the brightest daytime star is the sun. But Sirius is much brighter than all the other stars near it, and there are two reasons for it being so bright. It is just emitting a lot of light. It's about 25 times as luminous as the sun. And compared to most other stars you see in the sky, it's also very close, at about 8.5 light years away. As a matter of fact, it's the closest star you can see with the naked eye, easily anyway. That's not to say it's the closest star, aside from the sun. There are stars that are less than 8.5 light years away. For example, Proxima Centauri in the constellation Centaurus is 4.2 light years away. But all of those stars are almost impossible to see with an unaided eye. But Sirius stands out because it is so bright. So that's going to be the first object we look at tonight in the telescope, and here is the live view of Sirius. Now, you may be wondering, if Sirius is so bright, it's the brightest star in the sky. You can see it very well, even in cities. It's not hard to see at all. Then why are we really bothering looking at it in this program? Well, as it turns out, Sirius is actually not just one star, but two stars. We'll call Sirius A and Sirius B. And Sirius A is the bright one. Sirius B is a small companion star called a white dwarf. And I'm going to talk a little bit more about what white dwarfs are later, but they are kind of an embers of stars, of once larger stars. And in this case, this white dwarf, which is located right there, is about the size of the Earth, but the mass of the sun, which makes it an incredibly dense object. Now, among amateur astronomers, Sirius B, that tiny little speck, is notorious for being one of the most difficult objects for an amateur astronomer to see. It's not the most difficult, I don't think, but it is notorious for being very hard. So the reason it's so hard is not because Sirius B is faint, per se. It's that Sirius A, the big star, is so many hundreds, if not thousands of times brighter that Sirius B is almost completely lost in the glare. You can see it's kind of competing with the brightness of Sirius A. So it's a bit like trying to see something that is behind something that, or trying to see something behind a spotlight that's aimed directly at you. It's just so intensely bright. But right now is actually, as it turns out, a pretty good time to see Sirius B. Its orbit, its path, takes an elliptical path in the sky, and it is currently pretty far from Sirius A in an apparent distance in the sky. You can see it takes many decades for it to complete one full trip around, but right now in 2020, it's almost as far as it will get from Sirius A. So at the moment, next few years will be pretty easy to see it comparatively. Whereas in 2046, 2044, good luck. And you can see it there in that Hubble Space Telescope view. It's really, even then, it's pretty tough to point it out, but it is kind of on the upper left. And I'm going to go back to our live view. So Sirius B is so difficult because of the glare of Sirius A. That's what's making it so hard to see. And glare is something we've all experienced. Glare makes things hard to see in everyday life, too. I'm going to turn it back to Bill to talk a little more about that while I move on to our next object.
Sure, yeah. Sirius B being hidden in the glare of Sirius A is really a good analogy to what we see with unshielded outdoor light fixtures. This is kind of a classic demonstration of there's a backyard gate there at somebody's home with the floodlight aimed right at the camera. And the glare is hiding the human being that's standing in the gate. When you block out the bare light source, you're able to then see the person standing there. So glare actually impairs visibility at night. A lot of folks think the brighter the better, the more glare, the safer I am, but it's exactly the opposite. Here's another example. This is from a couple of friends of ours up in Midland, Texas, who changed out the carriage lamps either side of the front door of their home to be night sky friendly. The before image on the left, you can see the footprint of the light, or what I would call the light angel, coming out of the fixtures against the walls. You can see that the light is shining not just down, but also up the side of the building and lighting up the underside of the eaves. After the lights have been replaced with night sky friendly fixtures where the bulbs are recessed up under the hoods, there's still a nice ornamental carriage lamp, but the glare is dramatically reduced, and you can see that all along they had an American flag hanging in their front door, which was lost in the glare of the previous fixtures. So it's a great example.
All right. Thank you, Bill. Our next object we're going to look at tonight is known as Messier 47, M47. And I have this little neat zoom in here animation of where M47 is. M47 is an open star cluster, and it's one of many open star clusters visible at this time of year, all of which are kind of along the band of the Milky Way in the sky. Generally speaking, they're all going to be clustered around there. M47, the reason I picked it out to view tonight is because it is actually visible with the naked eye, although it's a little tough, but it is possible under dark skies to see the M47 kind of to the left of Sirius in the sky at the moment. There's also another cluster called M46 to the left. You just saw that go by. But that's the object we're going to look at live, this nice colorful group of stars. And here is the live view right now. So it's live from the telescope. And you can see there's quite a few stars. So M47, again, is an open star cluster. And open star clusters, generally speaking, are very, very bright stars, generally, and they are generally very young. There are usually a few dozen to a few hundred, maybe a few thousand stars in open star clusters. And in this cluster, we can see there's definitely more than a few. There's maybe a few hundred, but it's dominated by several bright stars. This cluster lies about 1,600 light years away. It's a lot further than Sirius, which is 8.5, right? So it took 1,600 years, roughly, for the light from these stars to reach us. And the reason that most open star clusters are young, in astronomical terms, is that all stars form in groups. They form in giant clouds of gas and dust. Looked at previous examples of that in previous sky tours. And over time, the gas and dust clears off, and what's left behind is essentially just the naked stars, like a young stellar family. But over time, over many hundreds of millions of years, the members of open star clusters will drift apart. They will not remain together forever. So therefore, if you see an open star cluster, it can't be all that old. In the case of this cluster, it's about 80 million years old, which sounds like a lot. But for comparison, our sun is about 4.6 billion years old with a B. These are only about 80 million with an M. So they're much younger. You can also note those colors in the stars, and the colors tell you several things about the star. But most importantly, they give you a clue as to the surface temperature. The hotter the star, the more blue it is. The cooler the star, the more orange or red. And you can see there's a nice orangey red star over here and several nice blue ones here. These bright blue ones, they are most likely more massive stars. The more massive they are, the shorter they live, and the sooner they run out of fuel and die. We're going to see an example of what happens there in a little bit. But that's another clue that these are relatively young stars, is you have very bright, young blue stars. Those just don't live all that long, so they have to be young. But again, the color tells you the temperature. We sometimes refer to that as you guessed it, color temperature. So to talk a little more about what color temperature really means and how it actually applies to everyday life, I'm going to hand it now back to Bill.
Thank you, Stephen. Yeah, there are no old blue stars. They die young. They burn up their fuel so fast. I think we have a graphic that illustrates color temperature. And it's a little different than in plumbing, where the red is hot and blue is cold on your faucets. In physics, it's actually the other way around. You'll notice the lower color temperatures on the left are more reddish in color. And as you go to the right and increase the color temperature, basically you're adding more and more blue content to the light output of a star or a light fixture. It turns out that more blue light, artificial blue light at night, is not good for us. Too much exposure to artificial blue light at night is going to disrupt circadian rhythm. So our goal is to keep outdoor lighting near the observatory at a color temperature of no more than about 2,700 degrees Kelvin, which has very little blue light content relative to much hotter sources. Daytime, by the way, is about 5,500 degrees Kelvin. That just a white, and then the hotter you get, the more blue there is. Something
That's not
died.
Good. Something died. Yep. I'll work on that. But Bill,
That's all right.
why is daytime 5,500 K? Why that value?
It's about the surface temperature of the sun. Not terribly surprising. We evolved in a diurnal cycle. All living creatures on the planet did. Daytime, nighttime, daytime, nighttime. And our eyes they operate differently in the daytime. They're sensitive to different colors of light than they are when our eyes are adjusted to the dark. In fact, daytime vision is referred to as photopic vision, and night vision is referred to as scotopic vision. And we're going to see an example of an object that we actually can take advantage of our scotopic vision to see colors through a telescope here in a little bit. But,
my application crashed, but it's almost back up and running. So just give me one quick second. A little longer than intended due to some technical issues. But the next object we're going to take a look at is known as Caldwell 25, also known as the Intergalactic Wanderer. It's kind of a fun name. And unlike what we just saw, M47, this is a very old cluster of stars, very massive, many stars, hundreds of thousands of stars, called a globular cluster. And I'm almost ready to show that view. Sorry, I apologize. Computers, that stuff happens. But it's almost back up here. And let's go. All right. So there is Caldwell 25, also known as the Intergalactic Wanderer. And this, as you can see, there's a lot of stars in there. They're packed together very tightly, and they are much fainter than the stars we saw before. So when I say the cluster, I really just mean the fuzzy ball here. This star is in the foreground. It's much closer than the cluster here. And this cluster contains, again, several hundred thousands of, maybe almost a million stars, which is a lot. And globular star clusters, they are, generally speaking, very old clusters. They are on the order of billions of years old as opposed to millions. And in this case, it is roughly 12 or so billion years old, which is very old, much older than most of these stars you see in the sky. So because it is old, therefore, it is made of mostly relatively smaller stars, because smaller stars consume fuel at a slower rate. They're more fuel efficient, and therefore they can live a longer time. And those smaller stars tend to be kind of reddish on the color spectrum. They do not appear nearly as blue as some of the stars we saw before. So this cluster, this globular cluster is one of over 100 globular clusters. And globular clusters mean in the Milky Way, and globular clusters are generally gravitationally bound. There's so many stars that gravity is keeping them together in one big kind of globe or sphere, as opposed to open clusters, which will generally drift apart over time. But this globular cluster is actually somewhat unique among all of the ones in the Milky Way, in that it is much further away than the rest at about 275,000 light years. That's a pretty healthy distance, 275,000 years for the light to reach us. And it's also a lot bigger than many other globular clusters. Many hundreds of thousands of stars, and it's over 200 to 300 light years across, whereas most other clusters like it are about half that size. And it's orbiting the Milky Way. It's orbiting the center point of our Milky Way galaxy, but much further out than all of the other clusters like it are. All the other globular clusters are kind of, a few 10,000, 50,000 light years from the middle of the galaxy. This one is 300,000. And that's why I earned the nickname the Intergalactic Wanderer, because it's sort of wandering through space between galaxies. Actually, that nickname's a little old. We now have learned a little more about it. It is most likely orbiting the Milky Way, just like the others. But the reason it's so far out, it's theorized, is because this was once the center of a much larger galaxy, which are like a dwarf galaxy or satellite galaxy of the Milky Way. So the Milky Way contains a few 100 billion stars, it's enormous, and every now and then smaller galaxies will drift near it and merge with it, or the smaller stars or some of their material will be drawn away. And what's left behind then is just the core, just that center point of the smaller galaxy, stripped of the rest of its stars by the Milky Way. So that's why this kind of that would explain a lot about why this cluster is so compact, so big, and so far away compared to the rest. All right, again, about 275,000 light years away from us. Pretty healthy distance. That our Milky Way is about 100,000-ish light years across. So we're looking kind of beyond the edge of the galaxy, kind of in the space between galaxies, but not still a long, long way to get to the next galaxy, many millions of light years. All right, Bill, I'm going to hand it back to you to talk a little bit about how seeing an object that's this faint is kind of a special thing.
Yeah, this is a great example of an object that you really need a dark sky to see. It would be visible through, say, an 8-inch telescope fairly readily under very dark skies. But if the sky background is brighter than this very low surface brightness object, it'll get lost in the soup, and you wouldn't see it. Regardless of the size of your telescope, the sky needs to be darker than the object that you're trying to look at.
I did want to also add that I have a Hubble Space Telescope picture of this cluster, so you can really see just how many stars are in there. Just an unbelievable amount of stars in this cluster. Breathtaking. Yeah, why is that important to research astronomy, though? I mean, if we have such big telescopes, then why can't we just work around the light pollution if we just gather more light?
Sure, sure. This is a nice image of the primary mirror of the Hobby-Eberly telescope, the 10-meter telescope here at McDonald Observatory. And it's an example of what we call a light bucket. It's basically designed to collect as many photons as possible from typically very faint objects. And in astronomy, faint often means very far away. In fact, one of the major experiments that this telescope is involved in is looking at galaxies out towards the edge of the observable universe to study dark energy. But it wouldn't be possible were it not for the darkness of our skies overhead here. We're talking about observations where maybe the HET, this 10-meter telescope, is collecting a couple of dozen photons per hour during its exposure. So You need really dark skies to see something that faint.
A dozen photons. Yeah, that's hard to wrap your mind around.
Yeah,
How many photons does a typical light bulb give off? In your household, just for comparison, like
countless.
countless, yeah, billions, trillions, quadrillions of
Yeah,
photons. And we're talking about trying to detect signals of less. You can count them on your hand how many photons. So you have to have a really big telescope, and you have to have dark skies in order to accomplish that. Um, all right, our next object tonight is known as the Ghost of Jupiter. That's its nickname. Its official name is NGC 3242. Not as memorable, but kind of has a ring to it at least. And the Ghost of Jupiter, it earned that nickname because it is kind of ghost-like, and it is about the same size of Jupiter in the sky. There it is. And again, that's roughly the same angular size as Jupiter in the sky, but it's much bigger than Jupiter in reality because it's very far away. Distance estimates vary considerably, but it could be in the neighborhood of around 4,000 to 5,000 light years away. And this is still a small object. So the Ghost of Jupiter is the remains of a dying sun-like star. So it was a star that used to be a lot like our sun today, but when stars similar to our sun run out of fuel, they puff up, expand, and blow off their outer layers into space. It's not an explosion, although you wouldn't want to be near it. It is a slow process unfolding over thousands of years, but I have a little animation of that sped up, so you don't have to wait thousands of years. But yeah, so stars, they puff up, they turn into red giants first. It's what our sun will become in about 4.5 billion years. And then that red giant sheds its outer layers, about half the mass of the star, more or less, is cast off into space, and the rest of the half collapses down inwards to form a white dwarf. And white dwarfs technically aren't true stars. They're not undergoing fusion at their cores, which is so some people define a star. They're just glowing from the heat and energy of being at the center of a star for many billions or millions of years, and also from being very dense and compressed. That'll also make things hot and thus white. So on that color temperature scale, the hotter something is, and I'll go back to that kind of scale, it'll be past the 10,000 K mark or so. So very, very whitish blue color to the star in there. But back to the live view. So that's what the star is at the middle. That's a dying sun-like star, white dwarf now. And we saw a white dwarf by itself orbiting Sirius A, so that was Sirius B. But around the star, we see that nebula, that cloudy bit. And that is called a planetary nebula. Planetary nebula meaning basically, well, early astronomers thought it looked a bit like a planet, but that's basically where the relationship begins and ends. It's not, frankly, all that great of a name. Doesn't really have all that much to do with planets. But you can see it is a very striking color, and it's got some structure to it. It's kind of a greenish blue or teal color. Here is a photo from the Hubble Space Telescope, and it's actually slightly false color in this image, but they did try to approximate the blue teal color. But you can see a bit more structure than we can see through our atmosphere on Earth with our telescope anyway. And you can see that's even got little red bits at the ends. So the star that died would likely lived many billions of years before it did die. But this process to form the shape that we see took place mostly in the last 5,000 to 10,000 years. It's actually estimated that the inner structure here is roughly 1,500 years old, 1,500 years old. And since it took maybe 4,000 or 5,000 years just for the light to reach us, we are seeing an outdated image, right? There's no way around that. The further away you look, the further back in time you look. So if you were closer to the star, this nebula now, you might see a very different structure in there. It would look quite different, most likely. It would still generally resemble this, but the inner structures and shapes may be changed quite a bit. Let's go back to our live view. And what makes this object interesting to me is that when you actually see it with your own eye in a telescope, especially a big telescope, it really does look almost exactly like that picture. And a lot of times in astronomy, the pictures are a lot better than what you actually get when you look through the telescope because of the limitations of the human eye, whereas these are long exposures, so we can take light over time and put it together to create a brighter image, more detailed image. And cameras just don't work like our eyes do. But in this case, it really does look like that. It's not quite as bright when you see it with your own eyeball on a telescope, the old-fashioned way. And usually, we don't see color when we look at objects in an eyepiece. We see mostly kind of grayish details. Some bright stars may have a little hint of color to them, but generally we don't see glorious color detail. Except this time, in this case, we do actually see a green color. And Bill, why is that? What is it about the human eye that allows us to see that?
Yeah, we spoke about it a little bit earlier, the difference between day vision and night vision. You're using a different set of receptors at night that are sensitive to this color of light, so it actually stands out quite well. This particular object is really a good analogy for a fluorescent light bulb, if you will. In fact, that teal color you're seeing is coming from oxygen fluorescing, excited by the energy being given up by the white dwarf, the core of that dead star, as it slowly cools. And as Stephen said, the sun will do something like this in about 4.5 billion years or so. So stick around, something to look forward to. But it does, that color of light is what your eye is most sensitive to at night.
So the color our eye is most sensitive to. But what happens then if you're why is it that the color, though? Why is that specifically the color we're most sensitive to?
Well, I'm not sure I know how to answer that, Stephen. I think you have something in mind.
Well, yeah, I mean, it's the color that we experience the most in kind of everyday life and under daylight conditions. We see blues and greens better because that's most of what is around us. That's what it's what our eyes kind of have evolved to be sensitive to, since it's such a common color to see in the middle of the day. But yeah, it's not common to see it brightly at night, and that's why it kind of stands out.
Thank you.
Yeah. All right, so I am moving on to our next object, which is located way over far from where we were pointed before, kind of over in the east, northeast. And I do actually want to add before I go there that the sky at the moment is really incredible. I just want to point out the live view of the sky. We have the faint band of the winter Milky Way, the last bit of the Milky Way over there. And we have Orion here, Sirius down there. And we also have this cone of light coming off. And that is actually natural. That's called the zodiacal light. And that brightish cone over there is dust in our solar system that's scattering sunlight back at us. So again, the zodiacal light. You have to be at a pretty dark location in order to see the zodiacal light. But once you see it, it's pretty hard to miss. You can see it's actually competing with the brightness of the Milky Way even. Really striking sky out there right now. But we're going to look at a striking galaxy next. I think one of the most famous galaxies in the sky, called the Whirlpool galaxy. It's over near the tail end of the Big Dipper. So there is the Big Dipper right there, also known as Ursa Major. It's the part of the larger constellation there. So kind of just off the tail end of the handle end of the Dipper, just above it lies the Whirlpool galaxy, Messier 51, M51. And so now I'm going to pull up our live view there in just a second. It's going to take me a minute or two to to get it running. And I don't know, Bill, any thoughts before I get that picture up?
Oh, the M51 is classic. The Whirlpool. It's a face-on spiral. It's very much what the Milky Way would look like. It's actually a little smaller than our galaxy, but the shape is very much what our Milky Way would look like if viewed from above or below. That is, looking at the disk of the galaxy face on. Um,
Yeah. All right. So I've just 3, 2, 1, getting those last few photons in on the camera. And all right, so there's our live view, and I'm going to make that image a lot better, so don't you worry. Let's stack it up here. All right, we're starting to see some details in there. All right, so again, this is M51, the Whirlpool galaxy. I'm trying to make this image as good as I can. Again, live from the telescope. And M51 is called the Whirlpool galaxy because of that wonderful spiral shape to it, which kind of does look like, I guess, a whirlpool. And M51 is roughly 31 million light years away, so 31 million years for the light to reach us. That's a lot further than anything else we've seen so far. And that means that we are looking back in time 31 million years. Now, whenever we would look at galaxies, aside from our own, the Milky Way, we're generally talking about millions of light years at the minimum. So 31 million isn't all that far in the grand scheme of things. This is still a relatively close galaxy, but yeah, we can see galaxies billions of light years away. But still, it's far enough that it is still very faint. Generally speaking, when we're looking at galaxies, they are challenging objects to observe because they are, generally speaking, very faint, and their light is spread out over a substantial area. So M51, again, it's 31 million light years away from us, and it's roughly, as you said, a little smaller than the Milky Way, about 60 to 70,000 light years across, depending on how you measure it from what point to what point. So our Milky Way is a little under 100,000 or 100 or a little more. So it's smaller than the Milky Way, but it is not actually one galaxy. It's two galaxies, two interacting galaxies, what we call M51A on top and M51B on the bottom. And you can see that there's even a sort of a bridge between them. It's a stream of stellar material, galaxies and stars, connecting the two. At least that's how it appears. And that's because M51B, the smaller one, is actually interacting with the larger one. It's passing near it, and in the process, the gravitational pull of the galaxies on each other are distorting their shapes. So over time, over many hundreds of millions or billions of years, as the two galaxies move around each other and their gravities pull on each other, that nice, pretty spiral shape will likely not survive. It will most likely deteriorate and get all messed up by the interactions between the two. As I kind of stretch the image a little more, bring out some more detail, you can see a little bit already of what I'm talking about. There is sort of faint streams, tidal streams, as we call them, on either side of these galaxies. That's one sign that they are actually interacting, as some of the stars, essentially, of these galaxies are being flung off away from them. You can also see a lot of dust and gas within these galaxies. If we zoom in, especially, you can see we can see a little pinkish spot, even a little bit, very subtle around there. That's a star-forming region, and also lots of gas and dust, mostly hydrogen and some other things too, from which stars are born. Basically, star fuel, raw ingredients yet to be turned into stars. But yeah, a breathtaking galaxy. It's a galaxy that is a favorite among amateur astronomers and observers visually, because it is relatively easy to find. And compared to many other galaxies, it's also still relatively bright. But that being said, it's still not a walk in the park to see it. It does require some fairly dark skies and a fairly large telescope, especially to see the bridge between the two and the faint tidal streams around it. And I don't know what happened to my image there. It's crashed once before. Maybe it'll crash again, but all right. Well, here is an even better image of previously taken, and you can see even better there the blue color from many young stars being formed in there. These are those pinkish regions that's really where we expect the most active star formation, as well as those streams I was talking about on the other side. And here is a shot from the Hubble Space Telescope of just the center, where you can see a lot of the dust and a lot of those pink star forming regions. But Bill, you've done some work looking at galaxies, even just the old-fashioned way with an eyepiece. Talk a little bit about that.
Yes, it's true. When I came to work here at the observatory back in 1990, I brought an 18-inch telescope with me, and hey, great. So we'll be able to get to the next target then, right? The Sombrero. That's something to look forward to. But yeah, I had an 18-inch telescope and took advantage of the dark skies here and embarked on a search for supernovae, exploding stars in other galaxies. And the Whirlpool M51 was one of my targets. I actually had about 1,200 different galaxies I would look at repeatedly, starting over about every 3 days or so to see if there was something in the field of view that wasn't there the last time I'd looked at it. And this is an example of a star. I mean, the Whirlpool probably contains on the order of 100 billion stars or so. And all you see is the combined light of all those as this soft glow. But in the image on the right, there's a star that looks like it's one of the foreground stars in the Milky Way, but is actually a star in the Whirlpool galaxy that exploded. And the message of that event arrived here in May of 2011. And this was detected with a digital camera and most likely with software subtraction to bring out the supernova. But this is it looks very familiar to me. I know the field quite well, actually. And yeah, I'd managed to discover 2 supernova visually and a couple more with a special CCD camera in later years. But right as I began my visual searches about the time that the digital revolution took hold in astronomy, and suddenly, instead of finding a dozen or a couple of dozen supernova per year, visually astronomers were finding hundreds and hundreds of supernova digitally with software.
Thank you, Bill. Yeah, I think that's just absolutely fascinating that you were able to find them visually. That's really shows some serious patience and dedication. But we're going to look at another galaxy the easy way with digital equipment, the cheap way. Doesn't require quite as much patience. And this galaxy is another very famous galaxy called the Sombrero galaxy, M104, Messier 104. And it is located kind of between the constellations of Corvus, the Crow, which is right around here, and Virgo on the left. You can see there are many galaxies up at this time of year that are rising over in the east. And this is part of what we call the Virgo cluster, Virgo supercluster of galaxies. And in fact, the Milky Way itself is part of this larger concentration of many galaxies. All right, so here's our live view, and luckily SharpCap didn't crash on me this time. But yeah, this is a live view of M104, the Sombrero galaxy. It's still kind of low in the sky, so it's not the ideal time to see it right now. It would be better if we waited just a little bit longer in the night, but we're impatient. So There it is. You can see it's got a very bright core, a very bright center, and then a dark line of dust dividing it. And if you want to see the sombrero shape, it is, well, it's upside down right now, but the bright core is the top of the hat, and this is the brim of the hat. I guess I'll buy it. It's better than some other nicknames I've heard of. Do you see a sombrero in there, Bill?
If I stand on my head, yeah.
Yeah, stand on your head. There's no up and down in space, so who's to really say. But I like the Whirlpool galaxy. This one is also about 31 million light years away. They happen to be pretty similar distances, although in completely different directions. And but in terms of composition, this is much different than M51, because M51, right? It was a nice spiral shape. It was interacting with another galaxy. It was very blue, very colorful. M104, the sombrero, by contrast, is a much yellower tone, which tells you that it is not forming a lot of new stars. They're mostly those smaller, dimmer stars. And we're seeing it at a different angle. So it's a disk that we're seeing almost edge on, whereas M51 we were seeing almost face on. And this also has a very, very bright core, much brighter than the core of the Whirlpool. And in fact, it's almost as bright as stars nearby. The center of the galaxy really stands out. I'm going to stretch the image just a little more, see what we can bring out. But the reason the core of the galaxy is so bright is because it is what we call an active galactic nucleus. And that means lying deep in the center of the Sombrero galaxy, there is a supermassive black hole, one that is actively consuming material. There's activity around it. And although black holes themselves are invisible, right, you can't really see them directly anyway, the areas around them tend to be very bright as material swirls around them and heats up from friction and can glow. So there's a lot of activity around the core, but the supermassive black hole itself is also just unusually large, even by supermassive black holes standards. It's about 1 billion times the mass of the sun by some estimates. That's big, even especially for the galaxy's size, which is about half the size of the Milky Way. So the supermassive black hole in the center of the Milky Way is maybe 4 or 5 million times the mass of the sun, whereas this is 1 billion. How did it get so big? Well, it's likely the result of mergers of several black holes, 2 or more over time by merging galaxies. So this galaxy, it likely is the result of mergers over many billions of years. Whereas in M51, we saw it was kind of actively interacting with another nearby galaxy. Give it enough time, they would merge together. In this example, they likely that process has unfolded many billions of years ago, and all appears quiet now. You can also see some background galaxies a little bit starting to come out. There's one over there. You really need some dark skies to see some of those. If I kind of pan around the image, you can start to see some other little faint fuzzy things that are hiding in the background. Those are other much more distant galaxies that are many hundreds of millions, perhaps reaching near 1 billion light years away. And if we look at a deeper image, you can see a little better what I'm talking about. Here's one taken earlier. You can see some more of those faint little background galaxies. And here's one by the Hubble Space Telescope, where you can really see the detail and the dust in there, as well as many other smaller galaxies dotting the background. I love images like that, where you just have lots of tiny little speckles of galaxies billions of light years away, each one probably as dramatic as M104 that we're seeing up close here. All right, go back to our live view here. Bill, you have anything to add about our view here before we move on?
Oh, it's simply spectacular, and the color response is really great with the telescope and camera system you have. It's very impressive, and this is a perfect example of the kind of object we like to refer to them technically as little fuzzy spots that you need a really dark sky to be able to make out with the telescope. So again, we're working very hard here at McDonald to keep the skies dark. We're actually we've applied to the International Dark Sky Association to establish hello cat to establish a an international dark sky reserve in the region. It would be the largest in the world if successful, if the application is successful. And part of that application process involves working with the surrounding communities to adopt night sky friendly lighting, basically lighting that's kept on the ground and out of the sky. This whole outdoor lighting dark sky effort is about dark skies, not dark grounds. We're not against outdoor lighting, but this illustration nicely sums up the steps from an unshielded, bright, glary light fixture that's shining light into the sky to one that's night sky friendly. Basically, it's a matter of shielding to catch all that wasted light and direct it down where you want it. Only illuminate the area that you're trying to see, not waste it off-site or waste it skyward. And then lowering the color temperature. Again, we talked about removing as much blue content as possible and still have it be useful for vision at night. So we're talking 2,700 degrees Kelvin. And then lowering the intensity, the output of the light fixture so that you're not using any more light than's necessary for the task at hand. It's very easy to overlight a facility. You might witness that at some gas station, the gas pump canopies on some gas station, convenience stores. And then lastly, adaptive controls where you're using timers or half-night photocells or motion sensors or a switch. A light switch is a wonderful thing for an outdoor light that's not in use, not serving any purpose at night. So this is what we're trying to do. Here's a great example of what it looks like on a large scale. This is an Apache Altus Midstream cryogenic complex north of Balmorhea, Texas. This image was actually taken with a drone a couple hundred feet up. And you'll notice that you don't see any bare light bulbs from above. The light is all shielded and directed downward. And the color temperature is also that warm white, 2,700 degrees Kelvin. We wanted to include this image because it demonstrates clearly that this type of night sky friendly lighting scales quite well up and down. I mean, it's appropriate for residential use, as you saw the home fixtures there, the image we showed earlier from the family in Midland, commercial lighting, businesses, all the way up to industrial lighting can be done in a night sky friendly way. And I will add that the people who work at these facilities that Apache and Altus have lit so nicely like it. They consider it to be better visibility for their nighttime activities. The glare has been dramatically reduced, and they can actually see the snake that they're about to step on. We've got testimonials from these folks that this is a significant improvement in visibility for their work at night.
All right, thank you, Bill. Again, yeah, happy International Dark Skies Week, everybody. This is going to wrap up our program. We do have some time for some questions, which some of the moderators have answered already, but some have been forwarded on to me. And the first question I saw was from W.H. King, who asks, how do astronomers determine how old these clusters or stars are by the color? The color is one way to determine the age of a cluster. It's a hint at least, but the best way is to use a technique called spectroscopy, where you take the light from the star and you break it apart into its component colors. And by analyzing the pattern of light, you can actually determine what stars are made out of, the different elements and the abundances in those stars. And generally speaking, old stars of very few elements heavier than hydrogen or helium. Very few, especially heavier than iron. And that's because in the early universe, there was basically just hydrogen and helium from which the first stars formed. And then when those stars die in their centers, they created heavier elements. And so when the star died, they spewed their contents out, which then got recycled to form the next generations of stars. So generally speaking, the newer stars have more metals and other things, whereas older stars tend to be very metal poor. And metal in astronomy is anything other than hydrogen or helium, because we like to annoy to annoy chemists. So yeah, spectroscopy would be the best way to determine that, and there are other clues, other information that would play into that too. Trevor Quinn asks, are there any optical filters in the image train? No, there is a UV and IR cut. That's it. Basically, I'm filtering out the ultraviolet and infrared because it would screw with the image a little bit, and I'm using the infrared on the guide camera. So I have a what's called the dichroic mirror in the optical train, which reflects the visible light to the camera, and the infrared light goes on to my guide camera. And that's what I use to keep the stars where they should be, because there's less atmospheric jiggling in the infrared. Yes, I'm filtering out the infrared and the UV, because UV can cause some weird image artifacts sometimes. Laura Gold asks, are M51A and M51B turning in the same direction or opposite directions? Their motions don't quite line up with what you would expect. M51A, the bigger one, the spiral one, is let me bring up a picture here. Yeah, okay. So it's the stars are going around they're going through the spiral arms per se. But the stars are generally going around in this direction. In this one, the whole galaxy isn't really going around with it. It's actually kind of moving through space. I forget what direction, but it's kind of making a big arc that's now passing nearby, but it will continue on in a longer trajectory that will take it away from the galaxy again. And actually, it's a bit behind M51. It looks like it lines up, but actually it's quite a bit further, just a little bit further away than the larger one. So if we were to view it at a different angle, they may not look quite as close. Kind of a line of sight effect. Aquapuncture asks, are there black holes in young galaxies, or are they always in old galaxies? Bill, do you want to take that one just for fun?
Well, my understanding is that there are likely black holes at the center of all galaxies, young and old. I think it's probably also safe to say that the older the galaxy, the more massive the black hole is likely to be, from having feasted on all the raw material in the vicinity, and perhaps from galaxy mergers. That would be my best guess.
Yeah, pretty much all of them do. Here's another question just came in from S.A. Cloudy. I understand the concept of gravitational lensing, but how do observers do this? Can anyone use gravity to magnify light from distant objects? I mean, technically, I guess. Technically you could. But to actually get a practical result doing it yourself, that's a different matter. Generally speaking, gravitational lenses in astronomy are chance alignments that we don't have any control over. It's just that one thing happens to line up on the same line of sight as something that's more distant. And the closer thing, its gravity, if it's very heavy, bends the light from the more distant thing around it and acts like a lens. So it's not something that it's not like a tool astronomers have. It's really something that we look for that naturally kind of happens in the universe by chance. maybe one day we'll learn how to harness it. There are some ideas to kind of use the sun as a giant gravitational lens and position a telescope on one side of the sun and to observe something that's opposite of it, but that's still a future technology being explored.
That what you're describing worked well enough to prove the general theory of relativity in
That's true.
1919.
That's true.
Yeah.
Yes. Yeah. But that was still a chance. It just happened that Mercury stars were in that line of sight. We didn't have control over it. We just kind of got lucky. Yes. But this is how we prove the theory of general relativity. One of the ways. All right. Well, I think that's about all the time we have for this evening. So again, thank you everybody for joining us, and happy Dark Skies Week. Thank you also to my moderators for helping us out. And clear skies, everybody. Have a good rest of your night.
Thanks, everyone.